Okay, so things you need to remember for this section is that temperature changes K values. Yes? Oh, by the way, how did the homework go? Did you guys have any questions from that? We're good? I would like to have a quiz on pH on Friday. Okay, I think I posted it on Teams.
Please send these runners to room 106 or 107 for pickup. Apple pickup.
Okay, so let's remind ourselves that if you have hydrogen and hydroxide equal to each other, then your solution is neutral. If you have a solution where hydrogen is greater than hydroxide, then your solution is acidic. And if you have a solution where hydroxide is bigger than hydrogen or the hydrogen is smaller than hydroxide, you have a basic solution. So we're just reminding ourselves of those three things, and we're reminding ourselves that temperature changes K values. So why does water, pure water, have a pH of 7? This question is actually misleading because pure water has a pH of 7 only at 25 degrees Celsius. Okay, room temperature. Okay, and this is the temperature at which Kw is equal to 1.0 times 10 to the negative 14. So to find pH, you must find the hydrogen ion concentration, right? We want to find pH. We need to find the hydrogen ion concentration, or hydronium, of course, because that is the same thing. And we know, because we can look it up if we need to, or we have memorized it, that Kw is 1.0 times 10 to the negative 14, and Kw is the constant for this equation here. What do we call that process where water turns into ions, or where you have two waters and you get H3O plus and OH minus? Tell your partner what we call that process. It's a big long word. Self-ionization of water. So instead of self, we're going to use auto. Auto-ionization of water. And it is from the auto-ionization of water that we get Kw. So Kw is going to be hydronium times hydroxide, or hydrogen times hydroxide. Yes, this is Kw. Now, in pure water, what do you know about hydrogen and hydroxide in pure water? Yeah, in pure water, concentration of hydroxide is the same as the concentration of hydrogen. So what we can do is we can say, well, let's take our hydrogen ion concentration and let's replace hydroxide with hydrogen because they're the same. Yes? So what that's going to give us is that's going to give us H squared is equal to 1 times 10 to the negative 14, okay? Or kW, yes? And that means that if we want to, we can take the square root of the entire thing, yes? And the square root of the other side, and we get H plus is equal to 1 times 10 to the negative 7 molar. And because hydrogen is the same as hydroxide, hydroxide is also 1 times 10 to the negative 7 molar. What is the pH? If hydrogen is 1 times 10 to the negative 7 molar, 1.00, let's just say. You guys should be able to do this in your head because this coefficient is a 1. If the coefficient is 1, you can do it in your head. If it's not a 1, you need to use probably your calculator, but it is a 1. So that's the same as saying, what is the pH if concentration of hydrogen is equal to 10 to the negative 7? What is the formula for finding pH? pH is equal to the negative of the log of concentration of hydrogen. So if we take the log of 10 to the negative 7, we get negative 7. And if we make it negative, then we get 7. Yes? What is our pOH? Also 7. Now let's assume that my kW value, I gave it 3 sig figs. Let's just assume that's correct. Okay. How should I write this pH value? Should I just write it as 7? 7.0003 sig figs. Okay. So that's at 25 degrees Celsius. pH is equal to 7. pOH is equal to 7 at 25 degrees Celsius. Anyway, I've written out the whole thing down there, and that's where we get that from. Is good? All right. Moving right along. Here we have a little table that shows the temperature dependence of kW. So you can notice on our left-hand side of the table, we have our temperature, and it's in degrees Celsius, and we start at 0 degrees. Our 25 degrees is here. We recognize kW is 1 times 10 to the negative 14. Yeah. And we just did the calculation that hydronium ion concentration is 1 times 10 to the negative 7 for pH for at 25 degrees Celsius. And I've done a bunch of the calculations because otherwise you're going to have to do too many calculations. It will become very tedious. But what I would like you to do is I would like you to see, can you calculate concentration of hydronium in pure water at 0 degrees Celsius, 10 degrees Celsius, and 20 degrees Celsius using the fact that you have the kW at each of those temperatures? I'd like you to try it. And if you're like, I have no idea, Ms. Spence, we just did it at 25 degrees Celsius. So you can use that one as a model. You can go back to your previous page and use that as a model. Okay? KW. Uh-huh. And what's KW equal to? Hydronium times hydroxide, right? Now, what substance are we dealing with here? We are dealing with pure water. Whoops, weeder? Water. And if we're dealing with pure water, what do we know? Hydronium is equal to? Yes. So watch this. Watch. Now, I don't know which side the temperature is on, but let's just pretend it's in the products, okay? Just pretend. If I increase the temperature, it will shift to the left. What will happen to hydronium? Decrease. What will happen to hydroxide? Decrease. By how much? The same amount. So the concentrations will remain equal. Okay, I'm not saying that the heat is in the products. I'm just saying, for example, you could also do the same thing if you put the heat in the reactants. Do you know what I mean? Okay, we'll come back to that later because we're actually going to use these values to determine is the heat in the products or is the heat in the reactants. So at any temperature, pure water, hydronium, and hydroxide are equal. So give that a try now. You know these two are equal. And that's how we were able to solve it on the previous page. Okay, so once you've got hydronium, you can start filling in hydroxide. That's okay. Okay, so what we've got is we've got KW is equal to H0 plus tensor. So far, so good? Okay. Now, we know that H0 plus is equal to OH minus. So what we're going to do is we're going to replace OH minus in the KW expression in that little box up there with another H3O plus because they are equal. Yeah, so we have H3O and H3O because it's neutral water. They're neutral, then hydrogen and hydroxide have to be the same because if you have more H, it would be acidic. If you have more OH, it would be basic. So it wouldn't be pure water. I mean, reactive. So now you know that this times this is equal to W. So in other words, this square that's how I would say okay, so are you okay with our So are you okay with the fact that you are equal? Okay, so what we're going to do is I believe the same, I think, for placement. So now what we have to do is have a PW. Yes. So if I take W
Square. I love being about it. Yeah, we'll understand. Yeah. A lot of things are just coming out. That is a problem. I was talking, I think so, you know, we have a beautiful. Other than, you know, you're actually like. QW is equal to H0 plus square. So it takes for you to get that, yes. That's all we're trying to do. We're not trying to do anything else with it. We're just trying to find out. Now, what was it even about? We're just trying to find a constant of real plus. There's no other difference on that. Okay. I want you to find H3 plus. Can you do that? Yeah, so if I know the vowel, if I know the number. Yeah. Okay, so what we're gonna do here is we are going to, and we've already done this for a second. Okay, because we also know that in pure water, concentration of hydrogen equal to the concentration of the it's not acidic, it's not basic, it's the same. So we can rewrite this as plus times plus.
Oh, since they're the same.
Yeah, since they're the same, I can rewrite it like that. Now, I could also rewrite that as H3O plus square.
Yeah.
Equals KW. And you know that that squared is equal to KW if you find that square. Yeah? Yeah, okay, good, that go. Ah, okay. So. Scientific notation. Okay, and then that's engineering mode because power tree, and three is like line or whatever. Yeah.
Do you know what I mean? Like, I don't know if that is what you want. Yes, so floating decimal means like normal notation, and then whatever that section is everything. I don't know why it's there. It's not after something, like, it's here, and then the last one is the. Yeah. See, you have a good calculator because you don't have to like load and then remember what number it is, you just have to go like. Yeah. Isn't that nice? Yeah. Okay, I think I've gotten around to a lot of you. If you have not yet figured it out, though, we're going to just talk through it real quick because we have here in pure water, H3O is the same as OH minus. So we're going to take OH minus and replace it with H3O plus, which means now that KW is equal to H3O plus times H3O plus, or we can write that as KW is equal to H3O plus squared, yes? And what that means is we can take the square root of both sides. So the square root of KW is equal to the concentration of H3O plus. Does that make sense? Okay. So this is for pure water. Obviously, if we added some acid or some base, that's not going to work anymore. But for pure water, this is what happens. So what you're going to do is you're going to take the square root of 1.14 times 10 to the negative 15. And you get 3.3. And I'm just going to throw in some decimal places, okay? 376 times 10 to the negative 8. Now remember, these two guys are the same. So this is also going to be 3.376 times 10 to the negative 8. Now, we're going to take the negative log of the concentration of H. So we're going to take 3.376 times 10 to the negative 8, and we're going to log it. And then we're going to make that, we're going to change the sign, and we get 7.472. Now let's check. Yes, I have 3 sig figs here, so I'm going to go with 3 sig figs there. Did you guys follow that? Yes.
Okay. Now, pOH, we're going to take the negative of the log of hydroxide. Oh, that's the same. So we'll get the same number, yes? So we'll get 7.472. What do we get if we add those two numbers together? We get 14.94. Now I have a question. What do you get if you take the negative log of KW? So what if you take the negative log of 1.14 times 10 to the negative 15? What do we get? We get 14.94. So we still have pH plus pOH equals pKW. Yes? Okay, so we're going to add a new column over on the end. We're going to add our pKW. All right, so If you are at a temperature that is not 25 degrees Celsius, pH plus pOH does not equal 14. It equals a different number. Just like hydrogen times hydroxide does not equal 1 times 10 to the negative 14. It equals a different number if you're not at 25 degrees Celsius. Okay, so if you've not done, calculate your pKWs. Try filling in the rest of it while you're here. 2.9, and I'll fill it in so you can check. And then the second half of the table should be easy because you just have to copy down the number. You don't have to actually do the calculation because these two are equal and the pH and the pOH are also equal. So I figured, having you take a square root for like 17 things was not necessarily a good use of your time. So these are all equal to each other. Now I would like you to try and figure out if the autoionization of water is endothermic or exothermic. Just like a question you might do on your equilibrium test, yes? Did we have one just like this on your equilibrium test? I think we did, didn't we? I feel like we did, didn't we? No? Maybe not. But it's very similar. You could have had a question like this on your equilibrium test. This one here, why? We haven't done one yet. But we didn't have this question on your equilibrium test. But we're just applying it to absence and basis. So what I'm saying is that this could have been a different question on your test. Because you already know how to do this. You know how to do this, right? If you're having trouble and you'd like to talk it over with me, call me over. Anyone want a little point in the right direction? Yeah? Okay. So, this, we want to go to the east from here, this is east from go. And what we're going to say is we know that as we increase the temperature, what's happening? Okay. The pH ultimately gets bigger, and the ion concentrations get bigger. Yes. It's shifting as we're increasing temperature. It's good? Yeah. If anyone would like to get themselves an apple, there are apples in that. Okay. And chat with me about what the answer to that question is. What do you think? What's happening is we're increasing the temperature. What's happening to our ion concentration is temperature gets bigger. Colliding. Okay, I want to know what is happening to the concentration. What's happening to the concentration as it gets higher and higher? Well, this is different than that. Yes, it is changing. Is it getting bigger or smaller? Bigger. Okay. So that's H plus concentration is increasing every time you increase the temperature. So if that's the case, which way is this improving? What do you increase the temperature? If it shifts left, are we increasing the up or are we making it like this? Up, so the concentration right there. Decrease. Does it decrease? No. Increase. Okay, so as the temperature goes up, the system shifts left, right? So this is why we get higher concentrations of ions. Okay, going that way. And actually, that way, when we increase temperature, yes. Okay. And that means the reaction.
Yeah.
So folks, what I'd like you to do is if you can figure out if it's and or exothermic, I would like you to try and write a coherent, clear explanation because you need practice writing coherent, clear explanations. Yes? So I would like you to try that and then check with the answer key. I will also do one up there in a couple minutes. Okay? Call me over if you have no idea whether it's endothermic or exothermic and you don't know where to start. Okay. Okay. So what we're going to do is we're going to say as we go down here, our temperature is increasing.
Yes? What is happening to our ion concentrations as they are increasing? So if we increase the temperature, the ion concentrations increase. So if we increase the temperature, frequencies react. Right, so which side is yours? Yes, it makes the ionization of water. You had a feeling, I know, right? You guys were pretty good. We're like, good. Okay, that's the right way to go. Yeah. Break yourself beyond what you think you are, that way you actually, actually, like, go with it, yeah. So now, not really. Your friend will let you not understand that explanation, are you going to over? Okay. And then I'm gonna come back and I'm gonna ask her and see if you guys do this stuff all the time. Okay. Very good. How are you? You're good? And then that's what? How are you doing? Good? Yeah. Well, okay, now, that's okay. Now, do you understand that you study? Okay, so stop again. We are this way, are we doing this way, or are we making separate waters? Yeah, if we're going this way, are we using the water, or are we making it? Tables. Making a product, I'll make it a non-part of it. I did not really, okay. So now what we're gonna say is, we're gonna here on our product, does the concentrate the actual increase? Are you gonna try and? Yeah, and if you're done with that, you can just work ahead, okay? Okay, so here we have our online here, as we go down the table, there's any data, yes? So as we go down our table, what's happening to the ion content? Getting smaller. This one and that one. Okay, oh, this one and that one. this one, and that one. Like that, so all of these are getting bigger as they change. Yeah. So. Temperatures getting higher. Ion concentrations are getting bigger. If the ion concentrations are getting bigger, which way is the equilibrium shifting? Left. So it's shifting this way. Are we making these or are we losing the power? If you're shifting that way, it's usually found in the big those. That's what shifting like. Is that you freeze these up and you make those. So if you were shifting left, what would happen to the concentration? What would you do? Are the concentrations equal? No, it hurts brains have to go down. Are which is equilibrium left? Right. Yeah. Okay. So we are making these. So we're making more rice. So it's true then, as we increase temperature, the amount of products increases. So where is that? It is still neutral. Stay going. Oh, just express it. Wait, 5 minutes. It's not bad. It's not bad. If you would like me to read your explanation and tell you if it's any good or not, or where it could use some changes, I can do that for you. Just going to put my pen back here and grab an actual pen. Hi. Yeah. Hi. Okay, so we got stuff. Yes? Okay. So if we look at this here, we say as we increase the temperature, right, it goes from 0 to 10 degrees, what's happening to our hydrogen concentration? It's getting bigger, okay? So when we increase the temperature, the ion concentration gets bigger, and these two are the same, so both of them would be getting bigger, yeah? Okay. So if these concentrations are getting bigger, which way is this equilibrium shifting? It's shifting to the right. So it shifts right when we increase temperature. Which side is the heat term on? Why is it shifting right? These concentrations are getting bigger. How did they get bigger? We take some water and we turn it into the ions. Does that make sense? So if we're shifting right, we're going to be making more of this, and so these will get larger. So if it is shifting to the right when we increase temperature, which side is the heat on? The reactant side. Does that make sense to you? Yeah, okay. Yeah. Okay. As temperature increases. Okay, yeah. Anyone want me to read their explanation or help them solve the problem? Okay. Why does he come over here? Yeah. Yes. Yes. Good. All right, okay, endothermic means pOH is increasing. Therefore, it is shifting right. So in science, we try not to use the word it, you would say the system. Is shifting right. And increasing temperature shifts a system in an endothermic direction. That for instance makes sense to you. Yeah. So if I increase temperature, the system wants to shift from the direction that it doesn't want. Yeah. Yeah. So if I increase temperature, it wants to shift in the direction that absorbs some of this less than 3 temperature. I don't understand how. Okay. Why is KW increasing? So remember that KW is concentration product is over concentration of the reactants. So if KW is getting bigger, your product concentration is bigger, which means you're shifting to the right. Okay. Side so that it absorbs. So you can say it that way as well. Yeah. How are you doing? How are you doing? When temperature increased, concentration. You like lost me like so long ago. Wait. Okay, here we go. Here. This is different. This is a different. Oh, this is. But this is okay. I think this is. Yeah. Don't say this is social center bonds. What happened to look? Also, there. Oh, okay. I was blind. Yeah. Like it was the same numbers, yeah. It's 3, right? Yes. 4. So add 1 more. Yeah, because wait a minute, I think that changed.
Okay. How are you doing?
Wait, why?
So how can you find H2O plus in pure water?
Oh, right, okay, there's more, okay.
Oh, how basic? It's not basic. Oh, what's wrong? Okay, okay. So, right, on the how to calculate the H3O plus in pure water. So that's what you're gonna start with. So how would you calculate H3O plus in pure water? That's okay, that's okay. You just did it. How did you find H3O plus? The KW. Damn. H3O plus is the square root of KW. Yeah. And it's not the H3O plus, it's continuing what you have now. Yes. Okay, so that's number one. What is true about H3O plus and OH plus in pure water? They're equal. Okay, so fill the rest of it along. Now, if these two are equal, what do you know about pure water? Yes. So, even though these pHs are not definite, right? This pH is not 7, right? So it's still neutral because these two are the same. Those are neutral as well. That's neutral pH at 50 degrees Celsius. That's neutral pH. Yeah? Yeah. Hello. Yes, as temperature increases, right? Yes, hi. pOH tells me the basis. Also, the lower the pH, just like the lower the pH, or do you just need to look at this one? You don't have to look at this one at all. Well, which is about 7 or below 7, right? So you look at it, you say below 7. Right, higher than that's basic. When it was acidic. So this I do more than less. So this is acidic. This is less than 10 to the negative 7, so it's bigger. This is less than 10 to the negative 7. It's just same way that it's less acidic. So you can also compare the neutral more higher than the oxide. So it's yeah, it's not really good as well. Right. So just keep going. And if you finish just homework, go back and do that. And we've got to put some cake on Friday. Just keep working on it. Okay? Okay, how's it going now? Yeah. You know what? I'm gonna do this with everybody. Okay, folks, actually if you have not successfully answered the questions at the bottom, we need to go through those in order for you to understand what to do in the exercises on the next page. Yes? So, we have our system. And are we all okay with it being an endothermic reaction? Anyone want me to come and explain it to them? Just call me over when I'm done here, okay? Now, write a formula for how to calculate the H3O plus in pure water. If we go back up here, remember, Kw is equal to H3O plus squared in pure water. So how would we calculate H3O plus concentration? We would take the square root of everything. So H3O plus is equal to the square root of Kw. Now tell me, what do you know about H3O plus and OH minus concentrations in pure water? They are the same. In other words, H3O plus is equal to OH minus. We have filled in the rest of the table. Now, at 50 degrees Celsius, is water acidic, basic, or neutral? So we're going to take a look. Here's 50 degrees Celsius. And we have a pH of 6.631. Does that make the solution acidic? Well, it would be tempting to say, oh, that's less than 7, so it's acidic. However, what do we know about the H plus and the OH minus? They are the same. And if they are the same, then it is neutral. Pure water at any temperature is always neutral. Pure water at any temperature is always neutral. And you're going to fill in the because. Try and fill in the because. Chat with your neighbor. See if you can fill in the because. At all temperatures, what is true? Concentration of hydrogen is equal to the concentration of hydroxide. At all temperatures, hydrogen equals hydroxide in pure water. And what do we know is true if H plus is equal to OH minus? The solution is neutral. Therefore, at different temperatures, neutral pH is not 7. Yes? is good? Okay, so your homework is going to be to finish off 4.2D. And if you didn't finish any of the previous one, finish that. If you feel like you need some extra practice, there's an extra practice in between there as well. Okay, tomorrow we're going to finish up pH and move on to some acid-base, some acid Ka calculations. That's what we're going to do tomorrow. I would like to finish the unit this week. That would be nice. And then on Monday, I would like to do a lab.
Oh, do a lab.
Because, or maybe it's not Monday, maybe it'll be Tuesday? What? It's a double block, so are we Tuesday? I think we're Tuesday. Yeah, Tuesday we're gonna look at a lab. 1 week. 1 week. Oh yeah, so we'll do it on Monday. You're scared you're going to exam like 1 day. Well, we're doing the exam next week, which is
You also forget to that.
yeah.
We would probably more chance before I done.
Yeah. Yeah. So next week we're gonna have a lab on Monday. Plus I'll answer some questions because you can always ask questions. It's a long block. The labs take the whole block. Yeah, I'll give you the review questions before we do. I would like your test to be next Thursday. Okay? Next Thursday. Yes? I feel like maybe like it's a little bit after.
Oh, I know.
See you twice. Right?
And you were right. The only problem has been, was backboard. So it makes sense.
Oh, or yeah, that should be H plus. I think I screwed that up, yeah.
Why would you?
So your homework, finish all of 4.2B and 4.2D, and you can do 4.2C if you want to. Okay?
I don't